You know, there's this paradox in the world of artificial intelligence right now that I feel like nobody in the mainstream is really talking about.
Yeah, it gets totally glossed over.
Right, because we see the headlines, right? We see the massive data centers, the billion-dollar clusters of GPUs and these models that are just getting smarter by the day.
Mm.
And I think we all just assume the bottleneck is always uh, the code.
Or the training data, like we just need more data.
Exactly. Or maybe having enough electricity to run the whole place.
Which is an issue, but yeah.
But there's a much more immediate, like, physical problem right inside the box. We're
Yeah.
building these incredibly dense, high-powered computer chips specifically for artificial superintelligence, or ASI, and then we are effectively just leaving half of them turned off.
Yeah, the dark silicon problem.
Right, dark silicon,
Yeah.
which sounds like a sci-fi villain, honestly.
It does.
But it's actually just a thermal limitation because we have the transistors, we have the architecture. But if we actually turned everything on at 100% capacity all at once, the chip wouldn't just crash, it would physically melt.
It would literally melt down. It creates a situation where we have what engineers call stranded capacity.
Okay.
It's like you've paid for the Ferrari, but you can only drive it in first gear because the engine block creates more heat than the radiator can actually handle.
Okay.
So you're artificially limiting the machine.
And today, for our deep dive, we're looking into a paper that claims to completely solve this. Not by building a bigger fan or, dunking the whole thing in a colder freezer, but by fundamentally changing the geometry of the chip itself.
Yeah, and it is an absolute fascinating paper. It was published just this month, February 2026, by Gallen Nasinjargo. And the title is a bit of a mouthful. It's called Infinite Fractal Descent, IFD, a universal fractal heat exchanger for 3D stacked ASI hardware.
Infinite fractal descent.
Yeah.
I mean, it sounds heavy, but the core idea, when you really dig into the source, is surprisingly grounded in something we see every single day.
Biology.
Biology, exactly. Nassim Jargal argues that traditional engineering, flat plates and fans and pumps, has essentially hit a wall. And to break through, we have to mimic the way nature solves heat and energy transport.
We need to stop building machines like rigid machines and start building them more like vascular systems, like veins.
So our mission for this deep dive is to unpack all of this for you. We're going to explore why our current chips are hitting this thermal wall, how this whole fractal solution actually works in practice, and why this might be the actual missing link that finally allows us to scale up to true superintelligence.
Because, as we'll see, it's really not just about cooling. It's fundamentally about the physics of entropy.
Right. So let's start with the problem itself, because computers have always gotten hot, right? My old laptop gets hot if I open too many tabs. Why is heat suddenly the one thing stopping ASI?
To understand that, you have to look at the geometry of how we build computers today. For the last 50 years, we followed Moore's law. We made transistors smaller and smaller, and we packed them onto a flat, 2D wafer of silicon.
The classic pancake chip.
The pancake, exactly. But we are hitting the absolute limits of physics on how small we can make those transistors now. We're down to atoms.
Right.
At the same time, we need these chips to be much, much faster for AI. Specifically, we need to reduce latency.
And latency is just the signal delay, right? The time it takes for a piece of information to get from point A to point B on the chip.
Yes. And inside a computer, the ultimate speed limit is the speed of light. So if you have a massive sprawling 2D chip, like a sprawling suburb, it actually takes a relatively long time for a signal to cross from one side of town to the other.
So you want to bring everyone closer together. You want to stop building suburbs and start building a skyscraper.
Precisely. You stack the chips vertically. This is what the industry calls a compute cube, or 3D stacked hardware. You put the memory right on top of the processor, layer after layer after layer. It cuts that physical distance down to almost nothing, so the speed is incredible.
But there's a massive catch.
A huge catch. In a suburb, a 2D chip, every single house has a roof that's exposed to the sky. You can put a fan on it and cool every transistor pretty easily.
Sure.
But in a skyscraper, the people living on the 50th floor are completely surrounded by other hot floors above them and below them.
They're totally insulated. They're trapped right in the core of the building.
And this leads to what the paper calls the scaling mismatch. It's a geometric trap. Heat is generated by the volume of the cube, but you can only cool it from the outside, from the surface area.
Oh, right. I remember this from high school physics. The square cube law. If you double the size of a cube, the volume, and therefore the heat it generates, grows way faster than the surface area.
Exactly. The volume increases by a factor of 8, but the surface area only increases by a factor of 4. So as you build these highly powerful 3D stacks, the inside just becomes a thermal trap. You physically cannot extract the heat fast enough through the outside walls.
Which brings us right back to dark silicon.
Right. Because you can't get the heat out, you literally have to throttle the chip. In modern high-density AI stacks, you might have to leave 40 to 50% of the silicon inactive or dark at any given nanosecond.
That is just wild to think about from an economic perspective. I mean, these tech companies are spending billions on these data centers, and effectively half of that investment is just sitting there doing absolutely nothing because we can't blow enough cold air on it.
That is the thermal wall. It's the single biggest barrier to ASI right now. You can't just throw more chips at the problem if you can't actually turn them on.
Okay, so that's the problem. We have a skyscraper that is fundamentally on fire, and we can't put it out from the outside. So Nissan Jargel's solution is infinite fractal descent. Break that down for us, because this isn't just drilling some holes in the silicon, is it?
No simple straight holes wouldn't work at all. The paper looks at how nature solves this exact problem. Think about your own body. You are a dense 3D volume just like the compute cube. Every single cell in your body needs oxygen, and every cell generates waste heat.
Right, and I definitely don't have a giant cooling fan strapped to my chest.
Exactly. You have a vascular system. You have a heart that pumps fluid through a branching network, arteries split into veins split into tiny capillaries, and there is a very specific mathematical rule that governs exactly how that splitting happens. It's called Murray's Law.
I saw that in the source material, actually. There was a formula. It was like d sub k plus 1 equals d sub k times 2 to the negative 1/3. It looks super complicated on the page.
It looks like advanced calculus, but the core concept is really just about laziness, or rather biological efficiency. Murray's Law is basically the mathematical sweet spot that allows fluids to branch out and cover a massive area with the absolute minimum amount of pumping energy.
Okay. So nature figured out the ultimate path of least resistance.
Exactly. If your blood vessels are too big, the blood moves too slowly and you waste a ton of space inside your body. If they're too small, your heart has to work way too hard to push the fluid through, and you'd burn up all your daily energy just trying to stay cool and oxygenated.
So Murray's Law creates the perfect structural balance.
Right. And IFD takes this exact biological law and applies it to the silicon stack.
Okay, so how do they actually build that into a chip?
They design what they call a recursive manifold. Imagine a main artery of coolant entering the compute cube at the top. That's level 0. It splits into smaller branches, which is level 1. Those split again. And the paper details how it goes down 10 distinct levels.
So by the time we hit level 10, we were talking about microscopic pipes.
We're talking about capillaries that are woven directly into the silicon substrate, right next to the individual transistors. It's fundamentally different from a cooling block sitting on top of the chip. The cooling is literally inside the chip.
I remember the paper mentioning the surface area gain from doing it this way is just massive.
It's exponential. By using this fractal branching, they increase the effective surface area for cooling by a factor of 10 to the 4th power. That is 10,000 times the surface area of a standard flat cooling plate.
10,000 times. That is unbelievable. So instead of trying to cool the outside of the building, they've basically run air conditioning ducts through the walls of every single room.
Even better than that, the fluid is essentially part of the wall structure itself. But getting the fluid down there is really only half the battle. This is where the paper dives into some incredibly intense fluid dynamics.
Right, because honestly, I assumed once you have the microscopic pipes, you just pump water through them and you're good to go. But the source spends a lot of time talking about internal rifling and vortices. Why is any of that necessary?
Because of something called the boundary layer. In thermodynamics, this is the enemy of all liquid cooling systems. When water flows through a perfectly smooth pipe, the water molecules right next to the wall of the pipe sort of stick to it. They move much slower than the water in the center.
They create like a film.
Yes, a stagnant film. And unfortunately, water is actually a pretty good thermal insulator. So that stagnant layer of water acts like a thermal blanket. It traps the heat in the metal wall and prevents the cool, fast-moving water in the middle of the pipe from ever grabbing it.
Wow, so you have the cooling water right there inches away, well, micrometers away, and it can't even touch the heat because of this microscopic blanket.
Exactly. You need to constantly scrub that blanket off, and that is exactly what the internal rifling does. In the tiniest capillaries, down at levels 8 through 10, They purposefully don't make the walls smooth. They actually print tiny grooves into them, spiraling down the inside of the tube.
Like the inside of a gun barrel.
Very similar shape, yeah, but for a totally different purpose. Those grooves, combined with the natural curves of the fractal branches, create what the paper calls synergistic vortex induction. Specifically, they create Dean vortices.
Dean vortices, which totally sounds like a 1950s rock band, by the way.
It really does, but in physics, it's basically a pair of counter-rotating vortices. Imagine two tiny tornadoes spinning in opposite directions inside the capillary.
Okay.
These tornadoes violently mix the fluid as it moves. They constantly scour the walls, completely stripping away that stagnant boundary layer.
So you've got fresh, cool water
Yeah.
constantly smashing directly against the hot metal.
Precisely. And the paper notes that this increases the Nusselt number, which is really just an engineering score for heat transfer efficiency, by 300%. It takes this lazy river and turns it into a high-pressure car wash.
Okay, so we've got the fractal veins, we've got the vortex tornadoes stripping the walls,
Yeah.
but there was one more layer to this, literally, because you still have to get the heat to travel from the silicon chip into the copper cooling structure in the first place, right?
Yes, the contact resistance problem. This is where the paper leaves fluid dynamics behind and briefly enters the quantum realm. You have a silicon chip and a copper cooling manifold. To you and me, if you press those two metals together, they look like they're touching perfectly.
But on a microscopic level, they aren't.
On an atomic level, it's like two rugged mountain ranges mashing together. There are huge gaps. And even where the peaks do touch, they are two totally different materials. And remember, heat travels as phonons.
Phonons, can you help visualize that for everyone?
Sure. Think of phonons as tiny localized packets of vibration. Heat is ultimately just atoms shaking. When those vibrations travel through the silicon and suddenly hit the copper, they encounter what is essentially a border crossing. Because the two materials have totally different atomic structures, the phonons literally bounce back.
It's like a traffic jam right at the border. The heat just gets stuck right at the interface between the two metals.
Exactly. Physicists call this Kapitsa resistance.
Yeah.
If you don't fix this bottleneck, it really doesn't matter how good your microscopic water cooling is, because the heat can't even get out of the silicon chip to reach the water.
So how does IFD solve that? Because I assume you can't just use thermal paste or glue them together at this scale.
No, thermal paste is way too thick and acts as an insulator at this level. Nasenjargel uses a process called nanosilver sintering.
Okay.
They take these silver nanoparticles, only about 20 nanometers wide, and they pack them between the silicon and the copper. But they don't just melt them, they sinter them under low pressure to create what they call a near monolithic bond.
Meaning, effectively, the silicon and the copper become one continuous piece of material.
Practically speaking, yes. It reduces joint fatigue by 60%, which is huge because hot things expand and crack over time. But they go even one step further. They add an atomic scale amorphous layer right at the boundary to smooth the transition.
An amorphous layer, what does that do?
It acts like a gradient ramp for those phonons. Instead of hitting a harsh wall and bouncing back, the vibrations just slide right across the interface into the copper. The paper states this enhances thermal conductance by a factor of 4.
It is just amazing how many different scientific disciplines are stacked on top of each other here. You need biology for the fractals, fluid dynamics for the tornadoes, and quantum mechanics for the silver sintering.
And you need incredibly advanced manufacturing to actually physically build the thing, which honestly might be the most surprising part of the whole paper. Because you couldn't build this even 5 years ago. You physically could not drill curved, rifled microscopic holes inside a solid block of metal.
Right, you can't get a drill bit to bend like a vein, so they have to 3D print it.
Yes. They use selective laser melting, or SLM. They use a specific copper chromium zirconium alloy. But here is my absolute favorite detail from the paper, and it's a bit of a happy accident.
Oh, I love a good engineering accident. What happened?
So in traditional machining, you always want everything perfect. Right, perfectly smooth, polished surfaces. But when you 3D print metal with lasers, it comes out a little bit gritty. It has this inherent surface roughness, about 5 to 10 micrometer.
Which usually in manufacturing you'd consider a flaw or a defect that needs to be sanded down.
Right. But in this highly specific case, that tiny bit of grit acts as a passive microturbulator.
Oh, it helps make the tornadoes.
Exactly. The roughness actually helps mix the fluid and spin up those Dean vortices. They basically turned a manufacturing limitation into a massive performance feature without having to do any extra machining.
That is just brilliant. So putting all this together, the fractals, the vortices, the nano-sintering. What does this actually do for the performance of the chip? What are the final numbers?
The benchmarks are completely staggering. The prototype demonstrates a heat flux capacity supporting over 1,000 watts.
And just for context for everyone listening,
That's enough to easily handle the thermal load of the next-generation Blackwell and Rubin-class GPUs. These are the absolute heavy hitters being built for ASI training right now. But the number that really matters here is the coefficient of performance.
that's the overall efficiency score.
Yes.
Yes.
It measures how much heat energy you are moving versus how much electrical energy you have to use to run the pumps to move it. A really good standard industrial chiller in a data center might have a COP of maybe 3 or 4.
Okay.
This Fractal system has a COP exceeding 10,000.
Wait, 10,000.
Yes. For every 1 watt of electricity you use to run the tiny pump, you move 10,000 watts of heat energy out of the chip. It is ridiculously efficient, specifically because of Murray's law. The pump barely has to work at all because the entire geometry is perfectly optimized for flow.
And that leads directly to the metric that everyone in Silicon Valley is obsessing over right now, which is tokens per watt.
The absolute currency of the AI age. We are moving into an era where high-level intelligence is just a utility commodity. If you can generate more tokens, more text, more code, more video generation, for the exact same electricity bill, you win the market.
So this isn't just about making AI faster. It's about making superintelligence economically viable at a global scale.
Exactly. This system reduces the pumping power overhead for a facility by 40%. That is a massive number for a data center operator. It's literally the difference between a highly profitable AI model and a total money pit.
And most importantly, it means the thermal wall is finally dismantled.
It is. We have successfully decoupled computational performance from physical volume. You can make the 3D stack as high and as dense as you want now.
No more dark silicon.
No more dark silicon. Every single transistor in the cube can fire at once.
It really changes your mental image of what a computer even is, because we are so used to thinking of chips as these dry, rigid, cold blocks of metal and silicon. But this description, it feels organic. It's pulsing with fluid. It has veins. It's exchanging heat almost exactly like a living thing.
And Sandberg actually touches on exactly that in the conclusion of the paper.
Yeah.
He writes about this massive paradigm shift from managing heat to integrating it.
Unpack that distinction for me a bit. Managing versus integrating.
Managing heat is purely reactive. The chip gets too hot, so you stick a bigger fan on it to fix the problem. You are basically fighting the physics of the box. Integrating heat means the fundamental design of the chip assumes the flow of entropy is just part of its existence. You optimize the matter itself to handle the energy flow from day one.
It's like the difference between wearing a heavy coat when it's cold outside and just evolving fur.
That is a great analogy. We are evolving the hardware. We aren't just building rigid boxes anymore. We are basically building synthetic organisms.
So if this actually works at scale, and the prototype data obviously suggests it does, what happens to the overall timeline for ASI?
It accelerates it drastically. The paper ends with a really profound thought that I think perfectly summarizes the whole situation we're in. It says that the arrival of true artificial superintelligence isn't defined by transistors anymore.
What is it defined by then?
It is defined by our ability to move entropy through space.
Wow, that's heavy.
Think about it fundamentally. Computation creates disorder. It creates heat. That is just the baseline law of thermodynamics. So the absolute limit of how much a system can think, how much pure computation you can do in one spot, is defined solely by how fast you can clear away that resulting disorder.
So Nazan Jargal is saying that cooling isn't just a side quest for engineers anymore, it's the main quest.
Exactly. He's saying that with IFD, we have finally solved the entropy transport problem. The rate of fluid descent through that fractal manifold now dictates the speed of thought for the machine.
It's like we've just built the circulatory system for a digital god.
Or at least for a very smart metal box.
Fair enough. But it does leave you with a really lingering, provocative thought to mull over. If we are starting to model our computers after our own biology, giving them vascular systems, maximizing their flow efficiency using the exact same math that governs our own veins, are we accidentally making them more like us than we originally intended?
Form follows function, right? If the ultimate function is high-level generalized intelligence, maybe the physical form inevitably has to look something like life. We might find that there's really only one optimal way in the universe to build a brain, and nature just figured it out a billion years ago. We're just now finally catching up.
That is definitely something for you to chew on next time you hear your laptop fan spinning up like a jet engine. It's trying its best, but it's fundamentally an evolutionary dead end.
Indeed. It's a dinosaur compared to this.
Huge thanks to Enkam Gallen Nasenjargal for publishing this incredible paper. It's not every day you get to read about the literal thermodynamics of the future. And thank you for coming on and helping us break all this down.
My pleasure. It was a really fascinating deep dive.
And thank you for listening. We'll catch you on the next deep dive. Stay cool.